Hello students, welcome to FosterJEE. This is our second lecture of electrostatics. In the last lecture, we have discussed some basics of electrostatics and very important Coulomb's law. In addition to that, we have also discussed one numerical based on Coulomb's law. Today, we'll solve some more problems on Coulomb's law and then we'll move forward to electric field. So, our first question is there any lower limit of the electrostatic force between two charges which are kept 1 meter apart. So the question is simple. We have to identify the lowest possible electrostatic force acting between two charges. Now let's start the solution. First of all, electrostatic force between any two charges kept at a distance r is written by Coulomb's law, which is F equals to K Q1 Q2 upon R square. In the problem, we are given that the distance between the two charges is 1 meter. Putting the value, we will get F equals to K Q1 and Q2. Now, we can also write that upon 1 square. So it's 1, so makes no difference. Now, we can see this force F depends upon both the charges Q1 and Q2, where this K is constant for a particular medium. That means if force has to be minimum or the lowest possible, because we are asked about lower limit. So force will be minimum if the product of both these charges is minimum. Now, we know that the lowest possible charge on any type of matter is E, which is the quantum of charge. Hence, if we consider both the charges as electrons or protons or one electron and one proton, the magnitude of charge will be same. So, in that case, our force will be minimum, and that is equal to Ke square. On putting the values, the value of K is 9 into 10 to the power 9 into the value of E is 1.6 into 10 to the power minus 19 whole square. On solving this, we will get 23 into 10 to the power minus 29 Newton. Hence, we can say this force F is the lowest possible force between two charges kept 1 meter apart. Now, a doubt arises that since there is a lower limit for force of electrostatics, is there any upper limit also? But till date, there is no such information about the maximum charge possible on the matter. So, for that reason, we can't define now the maximum limit of electrostatic force. But as we know that minimum charge possible on any matter is E, so the minimum force between any two charges will occur when both the charges carry charge equal to E, that is the quantum of charge. Now we'll take up another problem. The question is, suppose we have a rod of length L. Suppose its length is L, and a total of Q charge is distributed over its surface uniformly along its length. Now, suppose we have a point at a distance A from the near end of the rod. Suppose this is a charge of magnitude Q. Now, we have to find the total force of electrostatics acting between these two charges. Now, solution. The force of electrostatics will be K Q1 Q2 upon R square, where R is the distance between two charges. Now, immediately a doubt arises that if this charge is uniformly distributed over its length, then this part will have some charge, and this part also have some charge, this part also have some charge. Suppose these charges are equal, so as the length of these elements, these red elements. But all these elements are at different distances from this charge. So, which distance should we consider for evaluating the force? Now, if someone is not familiar with integration, we'll take up 2 minutes to discuss why actually we do integration. Now, suppose we want to calculate the force between these two objects. Suppose we'll take first initially this element, and its thickness is very small. So what will be the force between this particle and this charge? Only individual force of this. Forget about the rod at this time. If the distance between them is A1, then the force will be written as F1 equals to KQ. Suppose its charge is dq, which is not dq, but let us suppose it's q1. Then the force between this particle and this charge will be kq1 upon a1 square. Similarly, if we consider this particle, which is very near to this particle, then the force of attraction or force of interaction will be, if this charge is q2, then the force will be kq2 upon, if its distance is a2, then the force will be a2 square. Similarly, we will take many elements over this rod, and we can see once covering many such elements, whole rod will be covered, and the total net force will be F net equals to F1 plus F2 plus F3 plus up to Fn. Now, we can see if we leave these black spaces between them, that means this portion of the rod is not being considered. So, in that case, we will get some error. So, what does that mean? Suppose these are n elements that we have considered on this rod. Due to if n is small, then we will get many of these white portion. So, we will get huge error. Only in that case, if this n is very large, suppose limit n tends to infinity, only in that case the error will be minimum. But infinite, we can't do take up each and every element on this rod, that too very very small, and add up infinite times. So to do such calculations, we have a tool in mathematics which is called integration, which says f net will be the sum is being represented by integration symbol, and each element will be df, which is forced due to one such element at any general x. So we will get this f net. Now we will see how we do this. Now just I'm removing this to get some space, and also now this method of integration is applicable to almost 95% of the problems in physics. So it's very important at this point of time that we know how to do integration and where to do integration. Why are we doing integration here? Because charges are distributed over the rod, and due to uniform distribution, the distance between every charged particle is not same. So that's why in that case we will take one element from this charge q, which is at a distance x. Let's say the length of this element is dx, where dx is very small. This d is used for very small element, very small element. Now we will draw this whole thing downward, that we have this x, a charge q is placed here, and here we have one element whose length is dx. Now forget about this problem original. Now our problem is this one, only this one. Now we will write the force due to this small element. What will be the force? That is df. Why df? Because since it's very small element, the force also is very small. That's why we use df here. What will be the force? The force is k q, q1 upon x square. Why? Because the distance between them is x. Now what will be q1? q1 will be the charge on this particle. Now since in the question we were addressed that q is uniformly distributed over its length, so by unitary method we can say if q charge is distributed over L, that means L length have the charge q. One length will have the charge q upon L, and dx length will have the charge q upon L into dx. So this is the charge present on this particle. Hence q1 is q upon L dx. Substituting the value, we will get df equals to k q, q upon L dx upon x square equals to k q q upon L dx upon x square. Now from this expression over here, we know we have to add up all the elements, all such small elements, so that we can get the net force. And if we want to add infinite times or infinite number of forces, then we will use integration. So we will use integration here and also here, since this is a constant term. Now what is the value of integral df? Is f net, net force. So net force which we want equals to k q q upon L. Now carefully see the limits. When the value of x was a, that is, when the value of x was a, that is only this much. In that case, no element were being covered. No element, just right of this. So we can say no element is being covered. In that case, the force between this charge and any of the particle between this x, how much will be it? It will be 0 since no particle is being considered. So we'll write, if the distance is x and x is equal to a, the force will be 0. And when the value of x is a plus l, that is, we are considering now this whole. Hence, when the value of x is a plus l, in that case, full rod will be covered. Whole these elements will be covered. So, we will get the total force which we require. So, the value of when the value of x is a plus l, the force will be F net, and that we want. We can see this becomes F net minus 0, which is F net only, and this becomes integration dx upon x square a to a plus l. Evaluating this limit, we can get k q upon l. The integration of dx upon x square is minus 1 upon x. The limit is a plus l. On putting the limits, we will get k q upon l 1 upon a minus 1 upon a plus l. Or we can write F net equals to k q upon l a plus l minus a upon a into a plus l. We can see this a gets cancelled and this becomes k q l upon l a plus l. Also this l gets cancelled, so the net force becomes k q upon a into a plus l. So we can see this as result. Now comparing this with the force between any two particles of charge q and capital Q, that will be kq capital Q upon r square, where r is the distance between the two charges. From here we will conclude that F net equals to k q1 q2 upon r square is applicable when q1 and q2 are point charges. Point charges. Point charges means that its volume or size is negligible. No or negligible size, or we can say volume. In all other cases, we have to use integration. Now, my question is, what happens when we place any point charge q1 near another charge q2? Suppose initially they were very far away, they were separate. What happens when it comes closer to q1? Let us suppose they have some distance of let us suppose 1 meter. My question is, why only when it comes closer? Suppose initially the distance was very large, suppose that was infinity. So in that case the force will be k q1 q2 upon infinity square, and anything divided by infinity is 0. So initially force Fi is 0. Final force when it's come to 1 meter, in that case the force will be k q1 q2 upon 1 square, which is non-zero. So what happened when it comes closer to it? Why only after coming closer to q1, q2 experience some force? So its answer is simple, that q2 or q1 creates some electric field around it, and the intensity of electric field decreases as we move away from this charge. As we can say, these lines are fading. Now initially this was the case, and q2 was very far, so that their electric field was not overlapping with high intensities. Now once this q2 comes closer, then what happens is the electric field with much higher intensities gets overlapped. So that is the case of their electrostatic interaction. Now our next topic is electric field and how it's generated. So first we will define electric field. What is an electric field? So we can write it is the space around any charge in which another charge experiences some force. So it is the space created around any charge in which if we place some charge, they both will interact and exert some force on one another. So the main theme of this electric field, why we have defined electric field, is that two charges don't directly interact with each other. They produce some electric field, they both will produce some electric field, and they both electric fields will interact with each other. So the result of which is the both charges will experience some force. And also, as we have discussed in last lecture, that electric field is produced by both charges at rest or moving charge, or moving either with constant velocity and variable velocity. Now to define or calculate what impact will a charge exert over the other charge, it's important to define its strength. So our next point is electric field strength. Mathematically, it is the force experienced by unit positive charge is called electric field strength at a point. Now, to discuss with an example, we will draw electric field. Now, one thing we will mention that electric field strength is denoted by E. Now, for an example, suppose this is a region in which electric field of intensity E is traveling from this direction to this direction. Now, according to definition, if we place a unit positive charge in this region, unit positive charge, note that these lines doesn't mean that the field is existing only on these lines. In this region where lines are not there, just not to show for a clear diagram, otherwise the field is everywhere here. So let's suppose the charge is here and its magnitude is 1 coulomb, and that too positive. So by mathematical definition, E is the force experienced by unit charge, that is F upon Q. So if the charge is 1 coulomb, then this becomes E equals to F upon 1. So E equals to F. So this is the definition. If we place a unit positive charge in a region, then the amount of force experienced by it determines its strength. Now the point is, why do we place only positive charge? Why not negative? So its reason is, we will write positive charge moves, or we can write experiences force in the direction of electric field. And negative charge experience force opposite to the direction of electric field. Now, why does it so? It's the natural and fundamental property of charges. So we have to note that. Hence, we can say, if we place any charge, negative charge in this region, then the direction of force will be this, that is opposite to the direction of field, which is this. But if we place a positive charge in this region, the force will be in the direction of electric field. So if we place positive charge, then it determines the direction, that is the direction of force is same as the direction of electric field. So we can see, if we place any positive charge in the electric field region, then it will start moving because of some force. And if it is positive, then we know that in the direction it is moving, the net electric field is in that direction only. So this is the reason of placing positive charge. Now, since now we have noted that the direction of electric field is also important, so we can say that electric field is a vector quantity. Now we will discuss or see, is that like charges repel each other and unlike charges attract each other is justified by this statement or not. So let us suppose we have a positive charge here. Now, if it is point charge, then it will create electric field like this. Now, suppose this is the region in which the electric field is dominant. Now, suppose there is another charge placed here and its nature is positive. Then, what will be the force on this particle? Since electric field originates from this charge and travels like this far from it, hence we can see the direction of electric field is this, and the positive charge is present in this direction. So what will be the force in this charge? That will be in the direction of field. Hence we can see these both are repelling each other. So like charges repel is justified. Similarly, if we place any negative charge in this region, then the force will be to opposite from the electric field. So it's justified that unlike charges attract. Unlike charges attract. Now, one very important thing that we will discuss is, suppose we have a positive charge here. Now, electric field is always originated from this charge, that is positive charge, in every direction in 3D. So just imagine a sphere. It's emerging its electric field everywhere. On the other hand, if we have a negative charge, then all the electric field gets terminated on negative charges. So we can say electric field ends on negative charge. So we can see one more example where we have positive and negative charge present far from each other. In that case, electric field will be generated from this charge and will go to this charge. This will generate electric field from everywhere, and it will be terminated on negative charge. Now we are showing like this due to lack of space, but the field is emerging from positive charge and it's terminating on negative charge. Oh, sorry. This field lines are terminating on this charge. Now we'll move forward. We can write, first point is electric field originates from positive charge and gets terminated onto negative charge. Also, SI unit of electric field is Newton per Coulomb. We can see As we know, electric field strength is force acting per unit charge. The SI unit of force is Newton and the SI unit of charge is Coulomb. So it becomes Newton per Coulomb. Now, very quick example. Now, suppose an electric field and electric field of intensity 10 to the power 5 Newton per Coulomb exists in a region. What will be the force on plus 2 microcoulomb and minus 5 microcoulomb at this spot, or we can say at this region where the magnitude is 10 to the power 5 Newton per Coulomb. Now, we know electric field intensity is defined as force acting per unit charge, so the force will be Q times E, that is charge into electric field intensity. Now, for plus 2 microcoulomb, force will be 2 micro into electric field, that is 10 to the power 5. Solving this, we will get 2 into 10 to the power minus 6 into 10 to the power 5, that is 0.2 Newton. This is the magnitude of force, and this will act along the field, that is the direction of force and field, electric field is same on positive charge. Coming to negative charge, that is for minus 5 microcoulomb, force will be Q times E, that is 5 into 10 to the power minus 6 into 10 to the power 5, that is 0.5 Newton. And this will act opposite to the field. Now we will move to our next topic, that is electric field due to different shapes. Now, first is due to point charge. Since force is defined as, or else electric field is defined as force acting per unit charge. Suppose we have a charge capital Q and at a distance r. From this we have another charge small q. We have to find out what is the electric field due to this charge at a distance r. What we will do? We will place a point charge at a distance r and see what is the force acting on this particle, on this charge. So the force will be given by Coulomb's law, which is Q upon r square. Since electric field due to this capital Q is force acting on this charge upon Q, that is this charge. So our electric field becomes KQQ upon r square upon Q, which is KQ by r square, which is also written as 1 upon 4 pi epsilon naught Q upon r square. Since we know the value of K is 1 upon 4 pi epsilon naught. Now, what actually we have done? we need electric field produced by this charge at a distance r. So we placed a point charge at a distance r and calculated the force between the two, which is this. After that, we divided this force expression by the charge on which the force was written. So, in the result, we get the electric field due to this charge at any distance r. So, due to point charges, 1 upon 4 pi epsilon naught q upon r square. Now, our second shape is uniform ring. Uniform ring. Now, one thing I would like to highlight that we should never skip derivations, because the procedure involved in derivations helps a lot in tackling advanced problems. So, derivation is very important. Now, suppose we have a ring. Suppose we have a ring of radius r, and suppose this is our center, and from center a charge is placed, or not charge is placed, but we need electric field at distance x from its center. Now, we are given that a q charge is distributed uniformly over its circumference. So, due to this charge or this ring, we have to calculate for electric field on this point. Now, as discussed in earlier question, that since the charge is not a point charge and is distributed, so we have to use integration. Now, taking any element on this ring, we can see, suppose we take element at this place. Suppose this is our small element, very small element. First of all, we will calculate the distance of this element to the point of concern. Let us say this point is at a distance small r. Now, since it is perpendicular, because the ring is placed symmetrically with respect to this point. So, from every point on this ring taken anywhere, the distance of any part of this ring is same from this point. And what will be that distance? From Pythagoras theorem, we know r square equals to x square plus r square. Since this is r, so the value of r is root over x square plus r square. Now, suppose we take this element, very small element, which makes an angle d theta on this surface, d theta. Now, we will magnify this element. It will become like this if we draw it in 2D. This is a symmetrical ring. This is the center of our ring. Suppose our element is here. This is our element, and it subscribes angle d theta. So this is d theta. Now, as we are clear with the terminologies, so we can write the electric field due to this small element. Now, note that this is a very, very small element, so it will behave like a point charge. Now, what will be the electric field due to this point charge at this point? That will be k q. Let's suppose its charge is q1, k q1 upon r square, since it's at a distance r. Now, as discussed earlier, now we will forget every particle on ring. and we will consider that in this diagram only this part is present, and which is at a distance r from our point. This is a just to show, and this is our point. Now this is not a charge, because for electric field we know we want only one charge on whose electric field has to be determined. Now again, by unitary method, we know since it subscribes angle d theta on this ring. Now we are given that on whole circumference q charge is distributed. So we will write, if q charge is distributed over 2 pi angle, that is 2 pi radian, then on 1 radian the charge is q by 2 pi, and on d theta radian or d theta angle the charge will be q upon 2 pi into d theta. So this is the charge on this particle, which we have assumed as q1. So we will write q1 equals to q upon 2 pi d theta. Now for evaluating electric field, we will put the value of q1 in this expression. Hence dE becomes k, q1 is q upon 2 pi d theta upon r square, which is also equal to kq upon 2 pi d theta upon r square. Now the value of r square is x square plus capital R square. We will substitute and get dE equals to kq upon 2 pi d theta upon x square plus r square. Note that here everything is constant, here r is constant, only x is variable if we are given that x is changing. But since we are asked that we have to calculate at any x, that is x is given, so it's fixed, so everything is constant here. Now let it be our first equation. Now going to the diagram, we can see the direction. If it is q charge, let us say it's positive, then the direction of electric field at this point will be away from, that is away from this point charge. In this diagram, let's remove this diagram. In this diagram, the direction will be this. Suppose this angle is theta. No, we have taken this as theta, so let's suppose this angle is alpha. So by symmetry, this angle is also alpha. Now let's remove this. So if our small field dE is acting in this direction, what will be the force in perpendicular and along the center? In this direction, the field will be dE cos theta, cos alpha, because it makes an angle alpha. Then the electric field perpendicular to it is dE sin alpha. Now note that if we consider an element just opposite to this element along this ring, in that case the electric field from this part will be like this, and this component, since this will be dE only, so this component will be dE sin alpha, and this component of the field dE cos alpha will get added. So we can see the component away from the ring is getting added, but the component perpendicular to the ring is getting cancelled. That is, this will cancel this. Similarly, every part of this ring will cancel the electric field in any of this direction, that is radial direction. So we don't have to integrate this part, because we know the net electric field will be along this direction. So using this concept, we can write net electric field E net will be integration of dE cos alpha. Putting the value of dE, we get integration kq upon 2 pi d theta upon x square plus r square into cos alpha. Now, from this diagram, we can see the value of cos alpha is, the cos alpha is base upon hypotenuse. So, our base is x and hypotenuse is small r. So, we get the value of cos alpha as x upon r. So, we will substitute kq upon 2 pi d theta upon x square plus r square into x upon r. Remember that the value of r is root over x square plus r square. So put this value in this, we will get integration kq by 2 pi d theta x d theta upon x square plus r square whole power 3 upon 2, because its power is 1 and this power is 1 upon 2. Hence we are able to find the electric field due to uniform ring at any distance x. Now suppose this distance is dependent on x, that is this field is dependent on x. So we will write the expression as E equals to k q x upon x square plus r square whole power 3 upon 2. Suppose we want to find the maximum electric field. So what we will do for maximum at any distance, we will differentiate the electric field with respect to x. So we will get kq. Now we have to apply division rule for differentiation. We will get denominators square. This becomes cube. Now differentiation of numerator into denominator minus numerator as it is. The differentiation of numerator is x into 3 upon 2 x square plus r square power 1 upon 2. Now we have to set this value to 0. Hence we can see this becomes 0 and this one goes into this becomes also 0. Now we are left with x square plus r square power 3 upon 2 minus 3 upon 2x into x square plus r square power 1 upon 2 is equal to 0. Simplifying further, we will get x square plus r square power 3 upon 2 upon x square plus r square power 1 upon 2 is equal to 3 upon 2x, which becomes x square plus r square. Now we forgot to put 2x here because the differentiation of inner term will also come. So it becomes 2x times this. So this becomes 2x times this, which is equal to, which implies that x square plus r square is equal to 3x square. Simplifying further, we get r square is equal to 2x square, and from here we get the value of x is r is equal to plus minus root 2. So can we say if x becomes r upon root 2, the electric field will be maximum. That is, from this ring, if x becomes r upon root 2, in that point electric field will be maximum. And what is the value of electric field, maximum electric field? For that we have to substitute the value of x in this expression and calculate. On substituting, E equals to kqx, kq, the value of x is r upon root 2 upon r square plus x square, that is r upon 2, r square upon 2 whole power 3 upon 2. This becomes kq r upon r cube into 3 by 2 power 3 by 2 and also a root 2 here. On solving this, we get E max, maximum E as E naught, or else we can say 2 upon 3 root 3, that is cube root of 3 kq upon r square. So this is the value of maximum electric field. So in this lecture, we have started the topic for electric field due to different shapes, and we have covered due to point charge and due to uniform ring, and also due to uniform ring we have calculated the maximum value for electric field, at which distance it will occur, and what is the value of the maximum electric field. So I would advise to practice this derivation by your own and never skip derivation, as it clears many concepts. Thank you, and we'll